Welcome back to part 3 of your calculations topic. So far we've done empirical formula and molecular formula. We've done our gas calculations, and in this video we're going to work on percentage yield, which starts on page 18. So percentage yield is all about how effective our reaction has been, and quite often we expect that 100% of our reactants are going to react together and produce 100% of useful products. But actually in reality that's not true, and there's a few reasons here why that doesn't actually happen in reality. First of all, quite often your production of whatever product you're trying to make involves multiple steps with multiple pieces of apparatus. So we can lose product or reactants along the way in separation, either of the final product from the reaction mixture or in transfer between apparatus, or we could have side reactions going on. Those are reactions that we don't really want happening, and they take away from our main reaction. Therefore you're losing reactants, and therefore you're not going to get 100% of your desired products. And then also reversible reactions like our production of ammonia. We know that's an example of a reversible reaction. And so actually sometimes our product will be made, but then it will reverse and our product will turn back into reactant. So those are reasons why you might not get 100% yield at the end of your reaction. And the most calculations we've been doing up to now, they give us our theoretical yield. So if you've been asked what mass of whatever your product is will be formed using a certain amount of your reactants, the most calculations you've been using have got you your theoretical yield. How much in theory we could produce, but actually in reality that doesn't happen. The amount we get, the yield that we get in reality is called the actual yield, what we actually get out. And percentage yield just gives us a percentage of the actual yield compared to what the theoretical yield would be. So it's a very simple equation for this. Percentage yield is equal to actual yield. That's how much you actually get out, over theoretical yield times by 100%. And if we have a think about this equation, the values that we will get out will always be less than 100%. You might want to make a note of that. Will always be less than 100%, because your actual yield is always going to be smaller than your theoretical yield. So make sure your percentage yield values aren't over 100%. If they come out that way, you might have got your equation the wrong way round. So you can have a go now at exercise 5. It's just using that percentage yield equation. So percentage yield, I'll just abbreviate here to actual yield over theoretical yield times by 100%. So for question 1a there, I would write out the equation every time and get used to doing that in your exams as well. You can see there that your actual yield is 150. Your theoretical yield is 200 grams. Just make sure that your units of mass are always the same. So check that one's not in grams and one's in kilograms. So our actual yield is 150 grams. Again, write out your equation before you do this. Your theoretical yield is 200 grams and times by 100%. Put that into your calculator. You should get that your percentage yield is 75%. Okay, so you can do that for questions 1 to 4 there. Just be careful. In question 2, they give you some unnecessary information. Remember, all you need is the actual yield and the theoretical yield. Question 3, be careful of your units. One is in grams, one is in kilograms. You need to make sure you do that correctly. So have a go at exercise 5 now. Pause the video before moving on to the next section. This next section looks at calculating percentage yield when you've just been given the mass of a reactant. In other words, it's putting our normal moles calculations together with our percentage yield equation. It's just 2 steps, both of which you've done before. This is just the first time we're putting them together. So you're using normal moles calculations to work out the theoretical yield. As I said before, the moles calculations we've been doing up to now always give us the theoretical yield. In theory, how much of a product would you produce? And then use your equation to calculate the percentage yield. So we're going to do like that. Do these like we've always done before. We'll get given a mass of reactant. How do we convert to moles of reactant? Well, we use the equation N equals mass over RFM. We bring that over to our moles of product in our equation. How do we do that? Well, that's just simply going to be our balancing number ratio. Once we've got our number of moles of product, we can convert back to the mass of product. We do that by using the equation mass equals N times RFM. That gives us our theoretical yield. And then in the question, you'll be quoted your actual yield, the actual amount that they got out when they carried out this reaction. And so we put that into your equation. Percentage yield is actual yield, which will be given to you in the question, over your theoretical yield times by 100%. Again, this is best looked at with an example, and we'll do that over on page 20. So take a minute first to have a read at the question. You can see that we've got butane 1-ol, and your formulas and your RFM are given there. Are reacting with hydrogen bromide, created from sodium bromide and concentrated sulfuric acid, to give us bromobutane and water. So first of all, let's write the information we've been given underneath the relevant part of the equation. So we've been told that we start with 14.8 grams of butane 1-ol. That's 14.1, so 14.8 grams of butane 1-ol. And we've been given our RFM of butane 1-ol as 74. And sometimes it's helpful to either write it, if you've been given it, underneath your equation at this point, or to work it out at this point if you haven't been given it, so that later when we use our equations, we're ready to just put that value of RFM in. Okay, then you've been told we're converting that to 1 bromobutane with an RFM of 137. So that is what is going to be, we're working out our percentage yield of. So we need to work out the theoretical yield of 1 bromobutane. And we can see that our RFM is 137. So we work out our theoretical yield of bromobutane first of all, and then we put that into our equation. We can see we've been given a value of the mass of bromobutane that has been obtained, but that's not the theoretical yield. That is your actual yield. So it's good to identify it at that point, because sometimes you can think, oh, well, they've given me my mass of product. I don't actually need to do anything. So our first step is to convert our mass of reactant into moles of reactant. So we're going to use our equation, N equals mass over RFM. Our mass is 14.8. Our RFM is 74. Do this in your calculator along with me. That should give you 0.2 moles. Following our step-by-step method from the previous page, we now bring those number of moles over to our 1 bromobutane. We do that by using our ratio. You can see our balancing number ratio here is just simply 1 to 1. So that means I will produce 0.2 moles of my 1 bromobutane. I now need to work out the theoretical mass of my 1 bromobutane, so I use the equation mass equals N times RFM. Number of moles is 0.2, my RFM is 137. Put that into your calculator, you should get 27.4 grams. And just so we remember which value is which, this value that I've just calculated using my moles calculations is the theoretical yield. Now I have a value for the theoretical yield. I've been given a value of the actual yield in the question back up here, 17.8 grams. So now I'm ready to work out what my percentage yield is. We don't have much room left, but let's do it down here. Percentage yield is our actual yield over our theoretical yield times by 100%. Our actual yield is 17.8 grams. Our theoretical yield is 27.4 grams that I've just worked out using my moles calculations. We times that by 100%. Put that into your calculator, check that you get the right answer. It should come out as, I'll just squeeze it in here, it should come out as 65.0% if we round it to 1 decimal place. And quite often they expect you to do your percentage yield value to 1 decimal place. So that should come out as 65.0%. Okay, let's try one more example before you do a few yourself. Worked example 2. Again, you've got some organic chemicals that you've probably never met before, but that's okay, we just do it in exactly the same way. So in this reaction, we are converting phenol, which is our reactant, to trichlorophenol, which is our product, and our product gives us an actual yield of 488 grams. That's our actual yield. Again, it's good to identify that at this stage. How much reactant am I starting with? Well, I've got 250 grams of phenol. So I have 250 grams of my phenol. What's the RFM of phenol? You're probably better doing it at this stage. Well, I've got 6 carbons. It's going to be 12 times 6. And I have 6 hydrogens in total. So it's going to be 6 times 1. And I have 1 oxygen, so that's going to be 16. That gives you an RFM of 94. Okay, let's move over to our product that we're trying to work out the mass of, and that's our trichlorophenol. So I'll put a question mark there, trying to work out the number of grams of trichlorophenol. I am going to need my RFM when I come to convert to mass, so let's work that out now. Again, I have 6 carbons, so that's going to be 6 times by 12. I have 3 hydrogens in total, so that's 3 times 1. I have 3 chlorines, so it's going to be 3 times 35.5. And I have 1 oxygen, so it's just going to be plus 16. If you put that into your calculator, it should come out as 197.5 as your RFM. Great, so let's start our calculation. First of all, I need to work out the number of moles of phenol before I bring it over to my product. So I use the equation N equals mass over RFM, just as I did before. The mass is 250. My RFM is 94. That gives me a number of moles of 2.6597. Okay, and try and keep that as accurately as possible in your calculator. You could even store it, but if we just continue to use it, you can just work from there. So bringing that over to our product to work out the number of moles of product in theory that we produce. It's a 1-to-1 ratio again, and so in theory, I will produce 2.65957 moles of my trichlorophenol. I need to convert that back to mass, and I use the equation mass equals N times RFM, this time using the RFM of trichlorophenol. So that's going to be 2.65957. Try and keep it in your calculator if you can. And times by 197.5, the RFM that we worked out earlier. That gives us a theoretical yield of 525 grams. So if we circle that and write that that's our theoretical yield. Last step then is to work out our percentage yield. Percentage yield, again I'm going to abbreviate it, is actual yield over theoretical yield times by 100%. Our actual yield, which is given to us in the question we circled earlier, is 488 grams. Our theoretical yield is 525 grams that we worked out from our calculation, times by 100%. That should give us 93.0%, again to 1 decimal place. So again, we're just doing normal moles calculations to work out our theoretical yield and then putting that into our equation for percentage yield. So it's just about extracting information from the question, making sure that you've got the right mass of your reactants, which value is your actual yield, and so on. Over on the next page is exercise 6, more percentage yield calculations like we've just done so far. Just a couple of things to mention. First of all, just be careful of your ratios. The 2 examples that we did on page 20 were all 1-to-1 ratios, but that may not be the same for all of your questions. For question 1 and 2, notice that it's broken up into 2 parts. Part A, maximum mass, is just another way of saying theoretical yield. So it's just breaking it up into 2 parts. Calculate your theoretical yield first of all, and then put it into the equation for percentage yield. And that is for question 1 and 2. Then from question 3, it puts it all together. So it says, question 3, you're asked to calculate the theoretical yield. And then if 4 grams is produced, so that's going to be your actual yield. And then calculate your percentage yield. But again, just do it in exactly the same way. Question 4 is the one you need to be particularly careful about. And there's a reminder there at the end of the question anyway. But here, you've been given the mass of 2 of your reactants, 24 grams of iron oxide and 3 grams of carbon. So those are your 2 reactants. So what you need to do is work out your limiting reactant first, like we did back in Unit 1. And then calculate your theoretical yield from there. Use that number of moles. So, for example, you've got your 2 Fe2O3 plus 3 carbons. Remember, you need to work out your number of moles of each. And then to determine your limiting reactant, you need to divide by the stoichiometric ratio, or the balancing number, and essentially, so it will be moles divided by 2 for your iron oxide and moles divided by 3 for your carbon. Whatever number works out as the smaller is your limiting reactant, and you bring that number over to your iron. And just be careful, remember again when we were doing these, because you've already, say for example your limiting reactant works out as iron oxide, because you've already divided by 2, you just need to times by 4 then for your number of moles of iron, because technically your ratio is 2-to-4, but you've already done the dividing by 2 stage, so you just need to times by 4. So just be careful of that when you come to do question 4. So have a go at those now before moving on to the next examples. The next example we'll look at together, worked example 3, just includes some added complications. One which you will already have tried in that last exercise, the idea of working out the limiting reactant before then bringing that over to the number of moles of your product and working out your theoretical yield. So we'll do that in the next example, and we'll also look at this first complication, and that sometimes when we're working with organic liquids, we're given the volume rather than mass. There is no equation for volume and moles other than N equals CV, but that is using concentration. So what we need to do is work out the mass. So you need to go from volume to mass before you then go to moles. How do we do that? Well, to work out the mass, we use our density equation. Density, you'll maybe know from physics, is mass over volume. So mass is then going to be density times volume. So to convert from volume to mass, I do mass equals density times my volume. And then to go from mass to moles, I use N equals mass over RFM. So it's just an additional step, essentially. So let's have a look at worked example 3 to put those into practice. So worked example 3 talks about, again, these organic liquids you may never have met before, but that's fine. We'll work with the values that we've been given. We've got phenylamine being treated with ethanoic anhydride to produce N-phenyl ethanamide. So you can have a read at that question, but actually what hasn't been given to us are our density values, so you might want to write those in. For our phenylamine, our density, you can either write the word density or just a capital D, is 0.2 grams per centimetre cubed. And then for our ethanoic anhydride, our density value is 1.08 grams per centimetre cubed. Okay, so let's write all the information we have underneath our equation. So we've been told that we have 4.0 centimetres cubed of phenylamine. That's the second term here in our equation. So 4.0 centimetres cubed, of phenylamine. Our density is 1.02 grams per centimetre cubed. And later on we'll also need the RFM. So you can take a bit of time to work that out. You can pause the video and work that out yourself if you like, but it works out as 93 as our RFM. Okay, our ethanoic anhydride then is the next bit of information we've been given. We know that there's 6.0 centimetres cubed of that. Its density is 0.18 grams per centimetre cubed. And it's RFM. Again, if you want to work it out yourself, you can pause and do that, but it works out as 102. Okay, so what we need to do now is work out what our limiting reactant is of our two reactants that we've been given. So let's work with ethanoic anhydride first. So what we need to do, just as you've written at the top of the page, we need to use the equation mass equals density times volume. You can write it out in full if you like, to work out the mass before we then convert to moles. So our density is 1.08 grams per centimetre cubed and our volume is 6 centimetres cubed. That works out as 6.48 grams. I then use my moles equation. N equals mass over RFM. The mass, which we've just worked out, is 6.48 and our RFM is 102. That works out as 0.063529 moles. And again, you might want to store that in your calculator. Because it's limiting reactant, we need to divide by our balancing number ratio. And you can see that that is just 1 in this case. So our number of moles to compare which is our limiting reactant is 0.063529 moles. Okay, we need to do the same for phenylamine now. If you want to give this a go and try it yourself, you can pause the video and do that and then check that you've got the right answer before moving on. But we need to again work out our mass. First of all, mass is density times volume. Density is 1.02. Volume is 4 centimetres cubed. That works out as 4.08 grams. Plug that into your equation, N equals mass over RFM. Mass is 4.08. RFM, as we worked out earlier, is 93. That gives you a number of moles of 0.04387 moles. And again, I need to divide by my balancing number, which is just 1 again, which is 0.04387 moles. Okay, so I'm comparing these values to see which is the lowest to work out my limiting reactant, and you can see that that's my phenylamine. It has the lower mole value. So this is my limiting reactant, so I use it to bring over to my product to work out what my theoretical yield is. So I'm bringing it up to my N-phenyl ethanamide. You can see my ratio is just 1 to 1. I'm just timesing by 1 essentially, because there's no balancing number in front of the N-phenyl ethanamide. So my number of moles is 0.04387 moles. Okay, let's have a think about what we're doing here. Well, we're trying to work out the mass. So maybe I should have written this at the start, but we're working out the theoretical mass. And to do that, we'll need the RFM, which again, you can pause and calculate yourself, but it works out as 135. So to work out the theoretical yield, I'm going to use the equation mass equals N times RFM. My number of moles, try and keep it accurate in your calculator, is 0.04387. Moles times by your RFM is 135. And that gives me a mass of 5.92 grams. That is our theoretical yield. So now that I've got my theoretical yield, I simply need to put it into my equation to work out the percentage yield. Remember, percentage yield is actual yield over theoretical yield times by 100%. I've just worked out the theoretical yield. I need to look back to the question for my actual yield, which is 4.15 grams. That's your actual yield. So to work out my percentage yield, it's simply 4.15 grams divided by 5.92 grams times by 100%. Pop that into your calculator and that should come out as 70.1%. So just a couple of extra complications there, and you will put into practice the mass equals density times volume in the next examples. But where you're given two values for the reactants, you need to first of all work out which is your limiting reactant before working out your theoretical yield. So the last type of calculations you may be asked to do with percentage yield is essentially these calculations in reverse. So you may be given a percentage yield and asked to work out the mass or volume of a reactant needed to produce that particular mass of a product. So essentially you're doing these in reverse. You're being given the value of percentage yield and you're being asked to work backwards from that. So the first thing you need to do is work out the theoretical yield. In other words, what 100% yield would be, and then work backwards from there. So let's think about how we would calculate theoretical yield. Well, if percentage yield, I might actually write this at the top, if percentage yield is actual yield over theoretical yield times by 100%, we want to rearrange that equation to give us theoretical yield as the subject of the equation. So if I bring theoretical yield over to the left-hand side, I notice that it's on the bottom of the fraction on the right-hand side. Essentially, it's dividing. So it's going to be on the top when it's on the left-hand side. So theoretical yield is going to be actual yield. Then if I try and move my theoretical yield over, so essentially what I've done there is move my theoretical yield over to the top. Percentage yield is on the top here, in other words, multiplying. So it would actually be dividing on the right-hand side. It's going to be actual yield divided by percentage yield. And again, I haven't moved my 100%, so it's just times by 100%. Okay, if you need that explained further, I'll do it up here. So let's do it step by step. So we're rearranging this equation. We're bringing theoretical yield over to the left-hand side first of all. So that will be theoretical yield times by percentage yield. So theoretical yield is divided by on the right-hand side, so it's going to be multiply on the left-hand side when we bring it over. It's actual yield times by 100%. And then if I bring my percentage yield over to the other side, it's going to be theoretical yield is actual yield. Instead of it being multiplied on the left, it's now going to be divided by on the right and times by 100%. So you're essentially dividing your actual yield given in the question by the percentage yield and timesing by 100%. Because you're scaling it up to 100% essentially. Okay, and then we use our normal moles calculations to get our mass of reactant. Okay, so let's have a look at worked example 1 here, and we're going to need to write an equation. Okay, so we've got barium chloride solution. So let's write our equation first of all. So barium chloride solution, barium chloride is BaCl2 because barium is in group 2, so it has a valency of 2. Chloride is Cl with a valency of 1, so that gives us BaCl2. are reacting with an excess of sulfate ions. Sulfate ions are SO4, 2 minus. We're producing barium sulfate. Again, barium with a valency of 2, sulfate with a valency of 2. That cancels down to 1 to 1. So it's just BaSO4. And then what essentially has happened is the sulfate has replaced the chloride ions in your salt. So the chloride ions are essentially thrown out of the barium. So you're just left with 2 chloride ions. Okay, so before we make sense of this question, let's write down the information I've been given. So it says a certain volume of barium chloride solution of concentration 0.05 moles per decimeter cubed. So let's write that down. First of all, barium chloride is over here, so the concentration is 0.05 moles per decimeter cubed. And we'll use that later on. The precipitate of barium sulfate was dried and weighed. A mass of 0.52 was obtained. That is your actual yield. So we'll do that in green. Actual yield is 0.52 grams. The percentage yield is 80%. And we'll also need our RFM of this. Again, you can pause and work that out for yourself. But barium has a mass of 137, sulfate of 32, and oxygen of 16, but there's 4 of those. That gives you a total RFM of 233. And then what I am asked to work out is the volume of barium chloride solution required. So I'm going to put here, I'm working out the volume of barium chloride. Perfect, so look up to the top of the page. Your first step is to calculate the theoretical yield. We came up with an equation for that. That theoretical yield is equal to our actual yield divided by the percentage yield times by 100%. Our actual yield is 0.52 grams. Our percentage yield is 80%, timesing by 100%. Essentially, you get rid of your percentage signs there. And that gives you a theoretical yield of 0.65 grams. So if I was doing 100%, trying to make 100%, I would need to make 0.65 grams. And what you're doing here is you're essentially factoring in that there's only an 80% yield being given off. So actually you're going to need more of your reactant than if it was to fully convert. So I need to convert this to moles, and I do that using the equation N equals mass over RFM. The mass is 0.65 grams. Your RFM, which we worked out earlier, is 233. That gives you a number of moles of 2.789, and it continues on, times 10 to the minus 3 moles. I can bring that over now to my barium chloride solution. It's a 1-to-1 ratio. So the number of moles of barium chloride solution that I need are 2.789 times 10 to the minus 3 moles. Again, if you can keep that into your calculator to keep it as accurate as possible. Volume then, because I have a concentration, I'm going to use my equation, which we normally refer to as N equals CV. But rearrange that, we get the equation volume equals number of moles divided by concentration. Our number of moles is 2.789 times 10 to the minus 3 moles. Our concentration is 0.05 moles per decimeter cubed. I've kept my units in so you can see the units. We end up with volume. The value we end up with is 0.05579. If we think about units here, well, my units of moles are going to cancel out. And decimeter per decimeter cubed is going to now be up in the top line. and it's divided by decimeters to the -3. So my units are just simply decimeters to the +3, so decimeters cubed. So my volume is in decimeters cubed. You can see you've got a decimal value. So what you can do is times by 1,000 to put that in centimeters cubed, which would give you a value of 55.79 centimeters cubed. You can just leave it as decimeters cubed, that's fine, but it's maybe just a wee bit tidier to have it in centimeters cubed. Okay, so those types of calculations, you're working out your theoretical yield first of all. That's an important step. And then just doing normal moles calculations with whatever equation is appropriate. You can see on this side, we used our N equals mass over RFM. But on the left-hand side, because we were given a concentration, and because I was asked to work out the volume, I needed to use this moles equation. Volume equals N divided by concentration. Let's do one more example together before you try a few of your own. And again, if you feel ready, you can give this example a go yourself and then check that you've got the right answer, or you can work through it with me. Okay, so again, before we make sense of the question, let's write down what we have and what information we've been given. So we are making 1-bromobutane, it says at the start of the question, and we make that by reacting butane 1-ol with sodium bromide and concentrated sulfuric acid. Okay, here's the information we've been given. After purification, we've got 3.7 centimeters cubed. That's my actual yield of 1-bromobutane. So let's write that underneath our equation. So actual yield is 3.7 centimeters cubed. Of our 1-bromobutane has been produced. The percentage yield is 39%. And we've been asked to work out the volume of butane 1-ol. So I'm working out the volume of my butane 1-ol. Okay, the other information I've been given is our density values. First of all, butane 1-ol is 0.81 grams per centimetre cubed. 0.81 grams per centimetre cubed. Make sure you get them with the right formula. And also my density of bromobutane on the right hand side is 1.28 grams per centimetre cubed. That's my density value. Okay, and one other thing we'll need is our RFM of both of these things. We worked these out in a previous calculation, but again, you can pause and work them out if you like. And the RFM of bromobutane is 137. The RFM of our butane 1-ol is 74. Okay, we're ready to go now, and let's first of all work out our theoretical yield. So remember, back to step 1 on page 23, our previous page, is to work out the theoretical yield. We do that by taking our actual yield, dividing it by the percentage yield, and timesing by 100%. Essentially, I want to work out what 100% yield would be. So our actual yield is 3.7 centimetres cubed. Our percentage yield is 39%, and I'm scaling that up to 100%, so it times by 100%. Pop that into your calculator, it should come out as 9.487 centimetres cubed. Okay, I need to convert this to moles to bring it over to my butane 1-ol, but I can't, I haven't been given a concentration value. And this is just a liquid, so it's not a solution, so I wouldn't have a concentration value. So to convert it to mass, before I convert to moles, I need to use the equation mass equals my density times volume. Density is 1.28 grams per centimetres cubed. My volume is 9.487 centimetres cubed. You can see that those centimetres cubed cancel out, and I get left with a value of 12.1435, and so it continues on, grams. Again, keep that in your calculator if you can. Now it's time to convert to number of moles. N equals mass over RFM. Your mass is 12.1435. your RFM is 137, and that works out as 0.088639 if you've kept it accurate in your calculator. That's my number of moles. I want to bring that over to the other side to work out the number of moles of butanol that I would need in order to produce this mass of bromobutane. My ratio is 1:1. So I need 0.088639 moles of my butanol. The question asks me to work out the volume of butanol, but I can't go straight to the volume because I don't have an equation that links number of moles and volume other than concentration, but I don't have a concentration value. So I've got to convert to mass first of all. I do that by using the equation mass equals N times RFM. My number of moles is 0.088639. My RFM, as worked out earlier, is 74. Put that into your calculator, it should come out as 6.5593 grams. And then to work out the volume, I need to rearrange my density equation. Volume is equal to mass over density. My mass is 6.5593 grams. And my density is 0.81 grams per centimetres cubed. So my volume works out as 8.10 centimetres cubed. So plenty of steps in that calculation. But again, you're always starting by working out your theoretical yields. And we had the additional step there of being given density and volume values for our organic liquids. So that did require us an extra step. But you're always thinking each and every time, what information do I have? What moles equations do I have? And which one can I use at this point? Always trying to convert to moles to be able to bring it over to your reactant. And then convert back to either a mass or a volume, whatever your question has asked you for. Exercise 7 puts all what we've learnt about percentage yield together. A few of the different types of calculations. For question 1, it looks a bit complicated, but essentially you want to work out your number of moles of magnesium. Use your ratio to bring that over to your magnesium sulfate. That's just going to be 1:1 ratio. It's going to be the same number of moles of magnesium sulfate. Then you're bringing it down to your second equation. And again, that's going to be the same number of moles of your magnesium sulfate. Because you're bringing it to a separate equation, you don't use the balancing number ratio. You just take that as equal number of moles and then bring your number of moles over to your magnesium sulfate crystals, which again is just going to be a 1:1 ratio. This is your mass, your actual yield. So firstly you work out your theoretical yield using all these ratios, then put it into your equation. That's your actual yield, and that's of your magnesium sulfate crystals, which are MgSO4.7H2O. So when you're doing your RFM of that, be careful. Do your RFM of magnesium sulfate and then add on the RFM of 7 waters. That's going to be plus 7 times 18 at the end, because the RFM of water is 18. Question 2, just be careful. You've got your density values there of your silicon tetrachloride. You've got an option there. Either you can work out what the actual yield is in grams by using your density and your volume, or you could get your theoretical yield and convert it into a volume. So I would probably convert that actual yield into a mass, because that's what we're used to using with our percentage yield equation. So you would just be doing mass equals density times volume. Question 3 then is the example type that we were doing just a minute ago on page 24 and 23, where you've been given a percentage yield and you're asked to work backwards. Okay, magnesium is Mg, your nitric acid is HNO3. So your balance symbol equation is going to be Mg plus HNO3, giving you magnesium nitrate Magnesium nitrate is magnesium with a valency of 2. Nitrate is NO3 with a valency of 1. So you actually get Mg brackets NO3 2. When we react a metal with an acid, we always get hydrogen as our side product. And then to balance the equation, we need to put a 2 in front of our HNO3. So you're starting with your percentage yield of magnesium nitrate, 77%. And you're given the actual yield in the question of 12.7 grams. You need to work out your theoretical yield. And then work out your number of moles, bring it over to magnesium and calculate the mass that way. So have a go at those questions and you can email me if there's any problems. That's the end of your percentage yield calculations. So finish off those examples on page 25 before moving on to the last section, which looks at atom economy.